Okay, and I'm going to finish with talking about Great Plains prairie ecosystems. And this also sort of supporting some of what Dr. Lau was talking about. This is an image of the Great Plains prairies across Canada and the United States all the way down into Mexico. And this is about 1.7 million kilometers squared of land area. It's about 7 times the size of Wisconsin. I use Wisconsin, so I was born and raised there. Hope you can relate to the size of Wisconsin. Let's see. The light green is on the right-hand side is the tallgrass prairie. Then the dark green is mixed grass prairie, and then the sort of olivey color is shortgrass prairie. So that gives you the idea of the extent of this land area. And we have to keep in mind that in these prairie ecosystems, the majority of the carbon is again below ground. It's only putting up something on the order of 3 megagrams of carbon as biomass, but roots can produce about 8 to 15 megagrams of biomass, and that's about 35% carbon, so 35 to 40% carbon. So significantly more carbon is below ground. The prairie soils are about 70 to 130 megagrams carbon in the surface 20 centimeters of soil. So these soils stocked away enormous amounts of carbon in the A horizon over that 10,000 year period post-glaciation. It was not a rapid process to accumulate that carbon. And there's probably a lot more carbon at depth. In a native prairie soil, those A horizons stretch down 2.5 to 3 feet deep, okay? So that 70 to 130 is just in that surface 20 centimeters of soil. Okay, so what happened with land use change across the United States? We see that on this figure that we have the land area in thousands of hectares on the vertical axis, and then these bars, this is Illinois, Indiana, different states across the nation. This just tells you, here's the amount of historical tallgrass prairie in Iowa, okay? Here's the amount that is now in, that's in contemporary corn and soybeans. So 99% of Iowa's prairies were converted to cropland. The only one where you can see any tallgrass prairie is Kansas, and that's, they have areas like the Konza Prairie. So majority of that enormous land mass was converted to agriculture. And what happens when we convert it to agriculture, as many of you know, that disturbance rapidly leads to the loss of carbon. So as long as it took to form carbon, it goes really quickly. And what goes is the metabolic carbon. It's the carbon that's rapidly decomposed by microorganisms. And the humus carbon, the more passive carbon, remains at that new equilibrium which is reached in the system, not accounting for erosion at all. So lower total organic carbon by concentration in the cultivated soils and loss of soil structure. You can see the massive look to it, dependent on fertilizers. But at the same time, of course, you're producing crops as opposed to producing native prairie in a closed system, which of course was feeding ungulates and whatnot historically, and ungulates were being consumed, but that was a very much closed system. So here, I just give, this is a bunch of different studies and the depth of soil that was analyzed across all these prairie, paired comparisons of native prairie and agricultural land. And this just shows that most of these took place in the surface 30 centimeters of soil. No one was looking down at 2 meters deep. We need to go back and analyze these soils down to depth and see what sort of change actually took place. But these percent change in carbon is in this column, and you can see that it ends up, the average value for the sites, all these studies as a whole, is about minus 47%. So we lost about 50% of the carbon out of that surface horizon, again, not taking into account erosional losses. And as Dr. Lau suggested, that erosional loss doesn't just go into the ocean and be stored away as carbon down at depth. A significant amount, he suggested, quite a significant amount was being lost as emission, and some of it was being redeposited on the landscape. What were those land conversion rates like? I think this is really pretty disturbing and a little bit telling of the time. This is land conversion rates in millions of hectares per year. The purple bars are U.S. tallgrass prairie. The sort of brown bars are Brazilian Amazon. And the rates of conversion are disturbingly similar. About 2 million hectares per year were being converted over this period from 1870, actually well beyond 1900. But nonetheless, we had this massive conversion, and it's very similar to the Amazon. But of course, nobody was stopping and saying, what are we doing to the biodiversity of the Great Plains prairies? What are we doing to the soils? Because we were creating agricultural power at the time, right? And we still have it, but the disturbing part about it is that so much of it doesn't go directly into food production. 22% goes into, of corn production on the Great Plains is going into ethanol production. 70% is going into livestock feed. We can do a much better job of feeding ungulates, grass-feeding ungulates, and just finishing on grains, I would hope, and moving into the future. We have to do something about the distribution, how we're using the agricultural power anyhow. Well, so we released at least 5 petagrams of carbon in a 30-year period from that surface 20 centimeters of soil. Again, that doesn't account for erosion and doesn't account for carbon losses at depth. That's about 0.05 to 0.2 petagrams per year, which is, again, very similar to the Amazon. Probably the largest emitter at the time, definitely outpacing our fossil fuel emissions at the time. So, can we put the genie back in the bottle? We released it inadvertently. This is a really neat study by this guy, Kucharik at Wisconsin, that he was looking at a 65-year-old prairie restoration project and has a number of other prairie restoration studies going on. And just this is the relative amount, or excuse me, the total amount of carbon in the different layers of soil 0 to 10 down to 100 centimeters depth. And you can see that the prairie restoration isn't even close to catching up after 65 years. It's about half of the native prairie remnants. So it's a slow process. It is not a 60-year process to recapture all that carbon. Fossil fuels account for about 9.7 petagrams of carbon a year in net increased emissions. And deforestation somewhere around 2. So that, since the 1870s, the estimates that I'm working off of are about 390, which is quite similar to what Dr. Lal suggested, petagrams of carbon as fossil fuel and cement related emissions. Whereas land use change is estimated closer to about 160, but who knows? If we go back to 8,000 years, maybe it would be more like 400 or 500. But going from 1870 forward, about 160 petagrams of carbon. Soil carbon storage can increase, should increase. We do need to restore the health and vitality of our soils, but that difference is not going to match fossil fuel consumption rates, and we have to keep that in mind. So as we move forward here in the International Year of Soils, that our motto should be first do no harm and take soils as a focal point. I agree with Dr. Lal 100%. Soil scientists have a really, really important role to play in the food security and well-being of the world, and we have to emphasize the importance of soil as much, much more than as a carbon storage body. Soil additions, we can put soil carbon, we can build our soil carbon, but we have to keep in mind we are putting carbon back into the system. We are not accounting for our rampant consumption of fossil fuel carbon. They are not paired. They are not going to keep pace with one another, and we still have to put back what we pulled out. As we need to replace fossil fuel emissions, and that's something that really we need to keep saying. We need to say what are the alternatives and how do we get at them. The rest of the world, in terms of organisms on Earth, are solar powered. You can say that fossil fuels are originally solar powered. They were generated by solar energy, but hundreds of millions of years ago and accumulated over hundreds of millions of years. We are going to cook our goose if we continue to consume fossil fuels at the rate that we're consuming it. The rest of the world is solar powered. We can do it. You know, on the peninsula, the Olympic Peninsula in Washington, similar to BC, we grow trees faster than anywhere else in the nation, in our nation. And it is the cloudiest, murkiest place. I mean, that's where they filmed Twilight for the vampire. I mean, honestly. And the trees grow like mad. And so the efficiency for growing, for solar collection, we know we can do it. It's just a matter of putting our will to it. And we have to keep that on the front burner. We need to improve forest management, without a doubt, and we need to somehow manage to avoid these positive feedbacks on permafrost melting. At the rate we're going, we're not going to stop it. It's going to occur. And that positive feedback is what I'm suggesting is just the addition of carbon into the atmosphere from that, and then only warming it. And where possible, recapture carbon in the Great Plains.